students to our final section of Chapter 3 on linear programming. Linear program has many applications, and the basic idea behind it is you take a system of inequalities one step further. You graph a system of inequalities, that's your feasibility region. Then you locate all the corners of the feasibility region and test those corners in a linear expression used to evaluate the points and give the maximum minimums. So they're fairly complicated, but they start off with something we just did in the third section. That is systems of inequations. Now here's some of the applications, and we can thank Wikipedia for coming up with some of this information. We're going to do an example. I think there's several ones in manpower planning and so forth and economic management that we'll look at today. First, here's the basic idea. How do you maximize the expression 2x plus 3y on this feasibility region? First, I want to add some of the things that made this a region. That is, it's not just x equals 0, that's the boundary. I'm saying x must be greater than or equal to 0. Y is greater than or equal to 0. This is very common in application problems. But I'm going to have y be less than or equal to 0.5x plus 2 and y be less than negative x plus 5. So that we actually end up being below these lines. And so our feasibility region, the system of inequalities, solved to be this shaded blue area in here. And now we're going to find out what maximizes this expression by trying some points. So we can try the point like right here, 1, 2. 1, 2, 1, 2. If we put that in here, we get 2 and 6, which is 8. And we can try another point over here like 3, 1. 3, 1. And we get 6 and 3 is 9. So it seems to be getting better. But then if we step over here, 1.5, 2.5. 1.5, 2.5, we end up with, remember 2x plus 3y, so that's 3, and 7.5 is 10.5, but it's getting even better. But I think you can see that if I were to keep going, take any of these points and go up, it would keep getting better because it had more y's. Or keep going to the right because it had more x's. So that's why we're going to look at all the corners. 0, 0, like I said before. The corners will end up being the maximum of our feasibility region. 0, 2, 2, 3, and 5, 0. And when we look at these, we get 0 for that. 0, 2 only gives us 6. 2, 3 gives us 4 and 9, which is 13. That's our record so far. 5, 0 gives us 10. So there's your maximum. At 2, 3, notice it's a corner. You get your maximum value for the expression 2x plus 3y. Now don't always assume it's going to be the highest point. It's whatever maximizes this expression. So if the expression is 2x minus 3y, this would not be the maximum. Or it might be asked to minimize the expression. So keep that in mind. Now why do the corners always maximize or minimize? Here's a video to explain.
Well, I'm here to answer the question, why do the corners always maximum or minimize the expression? Well, the thing is, what we want to do is actually think about a third dimension, because that's what you're doing when you say like profit equals 2x plus 3y. So it's like z equals 2x plus 3y. It's a three-dimensional equation. But we're going to find out later on that this is always a plane in 3 space. So this little feasibility region, when I apply like a maximizing expression to it, it lifts it up into 3 space. So it's three-dimensional. Now take a look from this angle. You'll always see that no matter how I do it, one of the corners will always be highest. No matter how I twist this, I'll either get a whole edge that's the highest, or it'll be one of the corners will tip highest. That's because we're using linear expressions like 2x plus 3y, setting it equal to z, a third variable, and that also creates a plane. So there's no twisting or bending of the shape when it starts going in 3 dimensions. And as a result, the corners will always be at the highest value in your third dimension, which is either profit or z or whatever. Okay? Hope that gives you an idea of why that works.
Now let's try this on an actual word problem. And you'll find that there's several word problems listed for extra credit. They're recommended for like 2 people to do. You can sign up for those on the spreadsheet. Here's cars and trucks. Read through the problem and then start the video again. Okay, assume you read the problem. Let T equal the number of trucks produced per week, C equal the number of cars produced per week. Find equations for each sentence above. So shop 1 performs based on working 6 person days on each truck and only 3 on each car. So that's 6 times the number of trucks, 6 times T plus 3C. That gives the total number of person days used in shop 1. And shop 1, as we see later on, is limited to 150. So that must be less than or equal to 150. Shop 2, on the other hand, uses 4 person days on each kind of thing, car or truck. So 4 person days for each truck plus 4 person days for each car. Shop 2 is limited to 120 hours, so that's less than or equal to 120. And then that's our main expression. Now at the bottom here we have what's called the evaluating expression. The manufacturer wants to maximize profit. Let's call the profit P. And that's 500 per truck plus 350 per car. And that's sort of introducing a third variable. But first we can use these two plus the obvious, the number of trucks must be greater than or equal to 0 and the number of cars must be greater than or equal to 0 to come up with our feasibility region. And then I've done on the next page on GeoGebra already. Let me just tweak these a little bit. That is, x was greater than or equal to 0, y was greater than or equal to 0. In this case, I'm going to let x equal the number of trucks, and y will equal the number of cars. So this is trucks on this axis, and this is cars on this axis. So here's x and y as we go into our expression. And the expression from before was 500t plus 350c. So that's 500x plus 350c. Now also, these are both less than or equal to. And when you solve this system, we got many points of intersection, but we really only care about the feasibility region, and that's this in here. Below both lines, to the right of the y-axis, above the x-axis. So we're only interested in points in here, and the corners are going to be our key points. So the corners we're concerned with 0, 0. Of course, that doesn't give any profit. Why did you have a factory if it doesn't make anything? And then it looks like we have 25, 0, and 0, 30, and also point A, which is 20, 10. Let's crunch those out in the calculator. Okay, we've got them all calculated, and it looks like here's our winner. There's our winner. So we should make 20 trucks and 10 cars to give you this profit of $13,500 per week. Okay, that's it. Flange out.
This is my lovely wife and I, and we got trapped. Our house is right over there, but we're trapped by the rain. I know. I don't feel trapped.